Okay, we did this one yesterday. I mean, I showed you this problem yesterday. The charge flowing through a battery, in lecture 5, where the potential difference between the battery terminals is V. So you do delta Q times V over delta T. Notice you've got a current here, which is equal to IV, and then you can use that just like we do in the capacitance equations, where power, which is in joules per second, is equal to I times V, and many electrical are essentially resistors. Many electrical devices are. So you got P is equal to I times IR, which is equal to I squared R. Okay, there's voltage. Remember, V is equal to IR, Ohm's law, and then the inverse of Ohm's law, where you're getting rid of I. So Ohm's law is V equals IR. So I is equal to V over R. So V divided by R using Ohm, and you get V squared R. So you got these three equations for power, which make the problem easier to do. So here we go. Here's an example. You've got in the flashlight the current is 0.4 amps. All right, got the current. I, 0.4 amps, 0.4 times 10 to the negative 1 amps, or 0.4. The voltage is 3.0 volts. We want to find the power, and then we want to find the energy dissipated in the bulb in 5.5 minutes of operation. I think this would be a good place to start tomorrow, or on Friday. This would be a good one to start with on Friday. So this is what that would look like, because I think the students sometimes, and then we're going to look at the total energy at 5.5 minutes. Well, the power thing was pretty easy. Power is equal to IV. Nothing too crazy there. So that's 1.2 watts, right? When I multiply I and V together. V is equal to 3.0 volts, all right? But now, remember, power is equal to joules over per second. So if I run this thing, at the power would be constant, 1.2 watts, for 5.5 minutes, that would equal quite a bit of energy, probably, because 5.5 minutes is equal to 5.5 times 60 seconds, which would be 330 seconds. So you get 1.2 watts times 330 seconds, and that will equal whatever that comes out to be. I got to answer my